All right, before we start, one thing that's rapidly approaching is, believe it or not, the first exam, about 2 weeks from now. Did CASA open up the sign-up? Does anybody know? Okay, so I'm sure all of you are furiously getting your spots already. If not, make sure you do that soon because they do fill up. And we'll get you a spot, but it might not be the time that you prefer if you're waiting too long. So make sure you take care of that, and then I'll have some information towards the end of this week in class or via email or both about the first exam review session, which will be a little bit weird because of my schedule, but it'll be the only one that's kind of strange, and the rest will be on a normal schedule that I'll discuss later on. All right, but for today we're going to continue chapter 3. So as a reminder, the first exam covers the first 3 chapters of your book, and we're on pace to finish that about halfway through Thursday's class. So you'll have a week and a half or so to review all the material before the exam, so that should give you plenty of time to make sure you're on top of things. Today's topic is fairly important, as I'll get into, but first I wanted to start with the usual weekly reminder about study habits and course-related things that help you get a good grade in this class, which you're all interested in as well. So I'm gonna, I've already talked many times about the importance of doing all 4 homework attempts, and I regret to inform you that this broken record is not going to stop anytime soon. So here's some statistics. They're in Blackboard, but I'm guessing not a lot of you looked at them closely. These are from the spring 2019 semester about how people did in the course and how their homework habits related to their outcome in the course. So there were 444 students total that semester. Those are the ones that did not drop. I can't really keep track of the W's very well. Once they drop, they're out of Blackboard, and I have no idea what they did before they dropped. But the students that didn't drop, there were 444. That was a big section that year. 260 got A, B's, or C's. 184 of those got D's or F's. And if you look at sort of the average number of homework attempts for those 2 groups of students, the students that got the nominally passing grades A, B, or C averaged 3.4 attempts per week on the homework, and those that failed were only at 2.7, and there's a huge statistically significant difference between those 2 groups, so it's not noise. And then even I think a little bit more telling is if you break it down in sort of bands of how many homework attempts the students did per week and what their likelihood was of failing the course. So the students that did less than 1 homework attempt, I think there's only 1 student that was in that category, they failed. But as you can see, the students that only did 1 or 2 homework assignments per week, 68% of them failed the class. The students that did between 2 and 3, which is a pretty typical number, I would say, for us, but I want it to be higher, obviously, or I want this number to be lower. But anyway, that was 53%. But you can see the students that did between 3 and 4, only 33% of those got a D or F, and the students that followed my recommendation of doing all 4 homework attempts per week, only 26. Now that number's still higher than I would like, and there's other things that have to happen to drop this number down besides homework assignments. Although, not that you guys need to care about this, but from the university standpoint, this number would be fine. They're not happy with the number right now. That's not your problem to fix. That's my problem to fix. But anyway, this would be a number that they would be happy with. And if everybody did all 4 homework attempts per week, the data suggests that we would get down to that level. And then if other things were to improve, we could drop that even further. So there is a pretty significant correlation, I would say, between how many homework attempts per week you decide to do and the likelihood of you passing the course. Of course, there's more that goes into it. And as another reminder, if it wasn't obvious because you haven't had an exam yet, I wouldn't say the homework questions and the exam questions are identical, but there's some overlap and there's a lot of similarities. So if you do 48 homework questions per week, all 4 attempts, chances are you're going to see things that look a lot like the exam questions, and you're less likely to be caught off guard or surprised on the exam. So there's a lot of reasons for that, and putting good effort into it is important. So this is some statistics from a few years ago, before COVID, before everything got messed up for a couple of years, that sort of show that. All right. But what we're going to get into today is sort of the middle part of chapter 3, and we're going to sort of overlap with what we did last week. So I think Professor Larson covered for me on Thursday and said this is as far as he got. So I'll go over this slide again. It is in the recorded video that I posted, so this will be sort of a repeat of that. But this, I think, is the most important concept that we would have covered in the last lecture, this idea of bond polarity, which on its own is going to come up in homework questions and exam questions from chapter 3, and also is going to be relevant to some things that we talk about in chapter 4 as well. So it's important to have a good handle on it. So the key concept here is this delta En, difference in electronegativity. So if you have 2 atoms bonded together, A and B, let me change to blue. easier to see. So you've got two atoms bonding together, A and B. The difference in electronegativity, delta En, is just the absolute value of their two individual electronegativity values subtracted from one another. And again, it doesn't really have any significance if it's positive or negative. It's just the magnitude of that difference that we care about. We can, we have numerical tables and scales for electronegativity that sometimes will be provided if it's important, but other times you'll just need to use the periodic table to predict electronegativity differences. So electronegativity increases pretty smoothly as you go left to right and as you go bottom to top. So up towards the top right where fluorine is, that's the most electronegative. Bottom left, the periodic table, is least electronegative. Here, point that out on the periodic table since you can't all see the periodic table in the room. So it increases as you go in this diagonal direction here, bottom left to top right. So the further apart they are in those directions on the periodic table, the difference in electronegativity would then be larger. So a lot of questions will ask you to sort of predict that qualitatively, not giving you the exact numbers. So then within this, there's sort of two extremes. So the one extreme is perfectly covalent bonds. That's where the difference in electronegativity is 0. Now this is rigorously only true when you have the same atom bonded to itself. So carbon bonded to carbon, oxygen bonded to oxygen. So if it's the same atom bonded to itself, of course they have the same electronegativity because it's the same element, and then your difference in electronegativity is 0. So it's rigorously true when it's the same atom bonded to itself, but it can be approximately true for other combinations as well. So there are some, like carbon and iodine, I think, have almost identical electronegativity, at least to the 1 decimal place that they're reported. So those would effectively have a difference in electronegativity that's 0 as well. But when it's the same atom bonded to itself, you should definitely recognize that as being nonpolar. So when we have this situation, when the bond is perfectly covalent, when there's no difference in electronegativity, we say that the bond is nonpolar. And so that would be any of these diatomic molecules. H2, Cl2, O2. We'll learn today how to predict what the bond order is for molecules like this, or other more complicated things even, whether it's a single, double, or triple bond. Doesn't really matter. If it's the same atom bonded to itself, it's going to be nonpolar. Okay, so that's a perfectly covalent bond. That's one extreme in this difference in electronegativity. The other extreme is when you have significant differences, whether you would classify it as polar or ionic. And there's not really a strict divide between these two. There's really just one continuum from perfectly covalent on one side to ionic on the other, and everything else is in between. But sort of conventionally what we would refer to is if your difference in electronegativity is non-zero, but it's less than 2. So the electronegativity scale goes from about 0.7 from the lowest atom to like 4 for the highest. So if there's a significant difference that's bigger, that's around 0 to 2, we would typically call that a polar covalent bond. So it's still a covalent bond. There's still electrons being shared, but they're not being shared equally if there's a difference in electronegativity. And that's going to be true when you have two nonmetals bonded together. So nonmetals are the elements in the right side of the periodic table, and if you have two nonmetals bonded together but they have a significant difference in electronegativity, you would still classify that bond as covalent anytime it involves nonmetals, but if there's a difference, you would call it a polar covalent bond. And then if you have a difference in electronegativity that's bigger than 2, so a huge difference, we would conventionally call that ionic. And that's the situation where the electronegativity difference is so big that one atom shares or steals the electrons completely from the other, and you have a cation and an anion now that are held together in that way. And this is usually, or almost always in our case, going to be a metal and a nonmetal together. So when a metal bonds to a nonmetal, we would conventionally classify that as ionic, and it has a really big difference in electronegativity. But I want to emphasize, though, that there is no real cutoff between these. It's really just a continuum between the extreme of perfect covalent and ionic, and then polar covalent is sort of the in-between cases. So in reality, a continuum exists. There's no real distinction between covalent and ionic bonds. It's just a factor of how well the electrons are shared versus how much there's ionic character in that bond. And the other sort of terminology that we'll use on homework assignments is if you have a higher difference in electronegativity, that correlates with a larger percent ionic character. So you might see that in the Chapter 3 assignment, which is until next week. but if you see the term percent ionic character, that means how ionic the bond is, and that correlates with how big of a difference the electronegativity is. So those kind of all relate to each other. So this was sort of the closing slide from last Thursday, but it's probably a good summary of what the most important concepts are from that. All right, any questions on electronegativity before I move on? But the major topic for today, which is also important in its own right, is Lewis structures. And this is going to be two-dimensional representations of molecules that show how all the valence electrons are arranged, whether they're shared as bonds or whether they're non-bonding electrons, as we'll talk about as well. And this is important not only for Chapter 3, on its own, you're going to have to know how to do this and have homework and test questions related to it. But all the stuff we do in Chapter 4 coming up after this, which will not be covered until the second exam, all of that requires that you can do really good Lewis structures. So you have to be able to do this both for Chapter 3 and Chapter 4. If you can't do a Lewis structure, then the first half of Chapter 4 in particular, you're going to be lost. So make sure we learn it well right away. So what are Lewis structures? As I mentioned, they're two-dimensional representations of molecules. And they're typically only done for covalent molecules. So those are going to be molecules made up of nonmetal elements only. And what they show is all of the valence electrons. So we talked about in Chapter 2 how to determine how many valence electrons an atom has. Those are those outermost electrons, the ones that are in the highest principal quantum number typically. And then when atoms come together to make molecules, to form bonds, those valence electrons, as we have also talked about, are shared in covalent bonds. And so what a Lewis structure shows is how all of the valence electrons are arranged once the atoms come together and make that molecule. So what you have then is, in a Lewis structure, each atom is going to be represented by its atomic symbol. So that's just the abbreviation from the periodic table that represents that element. So you have an atomic symbol for each element, and then what you're going to show is the arrangement of the valence electrons around those atoms that are in the structure. All right, and so what you have then in terms of the electrons are two possibilities. You have bonding pairs. Those are the ones that are going to be shared in those covalent bonds, and those are going to be shown typically as lines. You can do them as dots as well, but lines is way more common. So we've talked a little bit about bonding pairs already, so that's nothing new for us, just showing those shared paired electrons as a line. Each line represents two electrons that are shared. But then you also are going to have something that we haven't really talked about yet, which are called lone pairs, or also called non-bonding pairs. So typically you don't have all of the valence electrons in the molecule being shared between atoms. In most cases, you're going to have some valence electrons that are not shared. They just belong to one atom in the structure, and these are going to be shown as dots, and they're going to be localized on whatever atom they belong to. So each pair will be two dots together. They're always going to be done as pairs, and these are electron pairs that are not involved in bonding. So they still are valence electrons. The Lewis structure needs to show all of the valence electrons. You can't leave any out. But there are going to be some in most cases that are not involved in bonding, and they're going to be localized on a single atom, not shared between two atoms like the bonding pairs are. So those are the features of a Lewis structure. Those are the three things you'll show. The atomic symbols for all the atoms that are in the molecule, lines for the bonds between those. Each pair of atoms will have at least one line between it that indicates that they're bonded to each other in that molecule. And then in almost every case, not every single case, but in most cases, you'll also have some non-bonding pairs that are localized on specific atoms in the structure. Okay, so let's go through then the steps for drawing a Lewis structure. We're going to cover it in a very methodical step-by-step process at first, so you can understand all the steps that go into it and sort of practice them in this sort of orderly way. In reality, as you do this more and more, you're going to get good at it, I hope, and you're going to, a lot of these things are going to become second nature and not necessarily need to be spelled out in this much detail. But again, just like anything in chemistry, it's one of those things you have to practice a lot. So when you get, by the time you get to the end of this section of the course, for many of you, you'll be able to draw Lewis structures without really thinking about all the steps individually. But there are still some key things you have to always keep in mind. So the first thing we have to do, because the Lewis structure shows all of the valence electrons, is we have to find how many there are. How many total valence electrons are there based on the chemical formula that we're given. So you add up the total for each atom, And we'll use the periodic table, as we'll see later on, to tell us how many valence electrons each atom has. And it's for main group atoms, especially main group elements, which is what we're dealing with, those in the p block primarily. It's very easy to do that, as we'll see. You have to remember to account for the number of each atom in the chemical formula. So sometimes you have more than one of a certain atom in the chemical formula, and so each of those is going to provide that number of valence electrons to the total. So you'll first look at the chemical formula to figure out how many of each atom there are, and then use that to help you add up the total number of valence electrons. So for example, if you have carbon dioxide, CO2, that 2 tells you that there's 2 oxygen atoms in the formula. So you would find the number of valence electrons for each oxygen atom from the periodic table, but then you would double that number and add it to the total, because there's 2 oxygen atoms in the formula, each one providing, as you'll see, 6 valence electrons for oxygen. All right, now there's one, I'm going to get this out of the way first. There's one element that you'll sometimes see in Lewis structures that is exceptionally easy to deal with, and that's going to be hydrogen. Hydrogen provides 1 valence electron. It only has 1 electron total, and that's a valence electron. But you don't have to really think about it much in Lewis structures, because hydrogen will always form 1 single bond, and that's it. Never forms a double or triple bond, never has non-bonding or lone pair electrons around it. It's just going to have a single bond, and then you're done with hydrogen. So I say this every time I teach this part of the course. If I don't really see you guys drawing too many Lewis structures, because these are all homework questions that are multiple choice typically. But if I see you drawing a Lewis structure that has a double bond to hydrogen or a lone pair on hydrogen, every time I see that, a small piece of me dies. So don't let that happen. All right, but that's hydrogen. So 1 valence electron to the total. Draw a single bond, and you're done. But then for the rest of the S and P block elements, remember that the way that we count valence electrons is those that have the highest principal quantum numbers, n being the principal quantum number. So it's all of the S and P electrons would count as valence electrons for those in the highest principal quantum number. But the nice thing is, from the periodic table, in the way that our periodic table is numbered in particular, you can just use the group number. So there's sort of 2 numbering schemes for the periodic table. We give you the old school one, but one of the reasons we do that is because the old school numbering scheme for the main group elements, those that are in the S and P blocks, the group number directly tells you what the number of valence electrons is. You have to be able to read Roman numerals, but I think you guys can all handle that. And that Roman numeral that labels the top of each column tells you how many valence electrons every atom in that column would have. So it's pretty simple in that case. So again, these valence ones are only those for the highest principal quantum number. Whatever the row of the periodic table that they're in sort of dictates that. It's however many of those there are. And then sometimes we're going to draw Lewis structures for things that have charges. As we'll talk about more formally, these are called polyatomic ions. These are groups of atoms bonded together, but they have a net positive or negative charge associated with them. And so you have to make sure you account for that when you're totaling up valence electrons. So if you're drawing an anion that has some amount of negative charge, you have to add electrons to the total, extra electrons for each negative charge. So in addition to the electrons that you would add up for each atom in the formula, you also have to then account for any extra charge that you have. And then similarly, if you have a positive charge, probably not as common for us, but we might see this sometimes, you would need to subtract electrons from the total for each positive charge. So you total up the number from the atoms, but if there's a positive charge, you take some of those away. Yes?
Well, we're looking at the D block, do you also count the S?
Yeah, so for the D block, it's S and D electrons in the last, but we don't do that for Lewis structures. That's why I didn't include it here. So you can't really draw Lewis structures for the D block. Take my class, my graduate class, and I'll teach you all about structures for the D block elements, but it's not as simple as a Lewis structure, unfortunately. So the Lewis structures that we draw are only going to involve P block elements primarily, maybe a little bit of S elements, you can do it as well, but it's mostly the P block, the non-metals, sort of covalent compounds. All right, so that's going to be, for our purposes for this section, we just need to worry about S and P electrons for valence. But yeah, the D electrons would count if it was a D block element. All right, so then what we're going to do is we're going to go through some progressive examples of how we apply all these steps. So I have 3 here that kind of show sort of different features of Lewis structure, so I'll go through each of these. All right, so if we go for this one here, PCl3, as I said, the number of valence electrons comes directly from the group number or from the configuration. So we did it with the full configuration, phosphorus and chlorine. If we find those on the periodic table, so the noble gas, phosphorus is here 15, chlorine is here 17, they're pretty close to each other. The noble gas that comes before each of those is neon, so those are the core electrons, which we don't care about. So neon would be in brackets as the core. And then the valence electrons were here in the 3rd row, so it's going to be 3s2, 3p1, 2, 3 for phosphorus, 3p1, 2, 3, 4, 5 for chlorine. So that would be, valence electrons would be 3s2 and then 3p3 for phosphorus, 3p5 for chlorine. So if we write out the full configuration, which you don't need to do, but I'll just show you that where it all comes from. For phosphorus, it's neon core, 3s2, 3p3. For chlorine, same core, 3s2 and this time 3p5. It's 2 over from phosphorus in the periodic table. All right, so if we write out the full configuration, again, the valence electrons are the ones that come outside of the core, the ones that have the highest principal quantum number, which in this case is 3. So for phosphorus, it's 2 plus 3, which is 5 total, 5 valence electrons. For chlorine, each one has 7, because there's 2 plus 5, 2 s electrons, 5 p electrons, all in the outer shell. So that's the valence electrons for those, but as I'll show you in a little bit, getting it from the group number is much simpler. So the total here, we have, in this formula, 1 phosphorus. There's no subscript on phosphorus, so it's just one of them. And then we have 3 chlorines. So we have each one of those is going to provide 7. So our Lewis structure for PCl3 will have a total of 26 valence electrons. All right, 5 from phosphorus, 7 from each of the 3 chlorines, total of 26. For the rest of these, I'll just use the group number on the periodic table, which makes things a little bit easier. So NO3-, which is called nitrate, as we'll learn next time. We have nitrogen and oxygen in the formula. Those are the two elements involved. So if we find those on the periodic table, nitrogen and oxygen right next to each other here, we don't even have to worry about the full configuration. Go up here to the group number, 5A, that Roman numeral V is a 5. 1, 2, 3, 4, 5, you just count the S and P blocks. So nitrogen has 5 valence electrons. Oxygen is in group 6. 6A is the sort of formal name for that, and that would mean it has 6 valence electrons. So without even worrying about the full configuration or figuring out which ones are valence and or not, just look at the group number. Group 5 for nitrogen, group 6 for oxygen, 5 valence electrons, 6 valence electrons. It's going to always be as simple as that for these types of problems. So nitrogen, there's 1 in the formula, and it provides 5 valence electrons. Oxygen, there's 3 of them in the formula, and each one is 6, because oxygen is group 6. So that's 18. Now the one thing we can't forget about those, as I said, if you have an overall charge, here we have a negative charge, 1 minus charge, we have to add 1 more electron for that. So the total in this case, 5 plus 18 plus 1 is 24. All right, so this NO3-, nitrate as it's called, has 24 valence electrons. And then finally, IF5. So this is what's called an interhalogen compound, 2 different halogen elements bonded together. I way down here in group 7, F way up here in group 7, top and bottom of group 7, but both are in the same column, so that means each of these atoms, the iodine and the 5 fluorines, provide 7 valence electrons because they're in group 7. All right, so group 7 is 7 valence electrons, and that means we have 1 iodine, which provides 7. We have 5 fluorines, which each provide 7. And so our total is 42. All right, so different numbers of valence electrons in all of these examples here, but we total them up using primarily the group number on the periodic table. All right, so any questions on counting valence electrons so far? That's a key step that you can't really skip. I mean, if you get really good at Lewis structures, you can kind of internalize it, but it's still important to keep that in mind. Because we want our final Lewis structure at the end to not have any more or any less than these numbers of valence electrons for each of these structures. Okay. All right. The next step is pretty trivial, but what you're going to do is you place the least electronegative atom in the center, and you draw a single bond to the other atoms. So this is going to be our next step. Now, in reality, people get hung up on, oh, what if I don't know what the least electronegative atom is? typically it's obvious from the formula. So PCl3, you put the 1 phosphorus at the center. NO3 minus, you put the 1 nitrogen at the center. IF5, the 1 iodine. So usually it's obvious what your central atom is just based on the formula. The one that there's 1 of is going to be your central atom. In cases where it's not obvious, we'll often specify it for you guys anyway, just to make it so that, you know, a little bit more straightforward for you on the exams. So usually you don't have to worry about what the central atom is. It's going to be obvious from the formula or sort of directly stated in the problem. But you're going to put your central atom at the middle, and you're going to draw single bonds to all the other atoms. So for PCl3, we would put phosphorus here in the middle, and you would draw a single bond to each chlorine. And at this point, shapes are arbitrary, so it doesn't really matter how you draw the bonds or what arrangement. Just spread them out a little bit, because you have to draw, you know, add more things to the structure eventually. But you just draw the center atom and then 3 single bonds in this case. NO3 minus, same story. 1 nitrogen at the center, 3 single, and we're not close to done yet, but this is sort of our first starting point. Now, technically speaking, too, when you're drawing Lewis structures for ions, you need to indicate the charge as well to make it totally correct. So you'll see either full brackets like that with a negative charge on the outside, or sometimes to save time and space, what I'll do is just draw like a little, you know, corner bracket like that and just a negative sign on the outside. But you need to technically indicate the charge. This is not really correct right now because we don't have all the electrons in there anyway, so calling this negatively charged is kind of stupid, but for good habit, we should include it. And then finally, IF5, we start with iodine in the center, and we're going to draw single bonds to all 5 of the fluorines in whatever random shape we want, just to spread everything out. All right, so that's the second step. That's probably the most trivial step of all. That's your sort of starting point for putting the structure together. You will have at least 1 single bond between each pair of atoms, you know, the central atom and all the outer atoms, and so you need to start with that. But then from there, we have to figure out what to do with all the rest of the electrons, because we totaled up on the last slide that there were, you know, 26 valence electrons for this guy. There were 24 valence electrons for this, and there was 42 for this one. And we haven't come anywhere close to using all of those just by drawing these bonds. So we have to figure out what to do with the rest of them, and that's where the next steps come into play. So the first thing we're going to do is we're going to distribute all the remaining electrons as lone pairs. So however many electrons we have left after drawing those bonds in the structure go initially as lone pairs. They won't necessarily stay as lone pairs the whole time, but that's how we're going to start. And so the first thing we do is what's called completing the octet. We'll define what this means more carefully in a second, but we're going to complete the octet first of all of the outer atoms. And we do that by adding enough lone pairs to each of them that they complete their octet. So what does it mean to complete an octet? Well, the octet rule, as it's called, means that for every atom in the structure, and particularly for the outer atoms that we're starting with here, you want the number of bonding and non-bonding electrons together to add up to 8. So you want each atom, each outer atom specifically that we're dealing with initially, you want each of those outer atoms to have exactly 8 electrons around it. Two of those would be from the bond to the center atom, then the other 6 coming from typically lone pairs, at least at this initial stage. All right, so that's what it means to complete the octet or to follow the octet rule. And for the outer atoms, you're always going to want to do that. As we'll see, sometimes the central atom doesn't follow the octet rule. We'll give examples of when that is and how to identify when that's okay. But for the outer atoms in the structure, those on the outside, you want exactly 8 electrons around them, from the bonds and from any non-bonding electrons they have. So at that point, if you still have leftover electrons, even this won't always use up all of them, whatever's left over still, you're going to add to the central atom as a lone pair. So you don't add lone pairs to the central atom until the very end to use up whatever remaining electrons you have. Now, in terms of the central atom, though, what we have to recognize is that it doesn't always follow the octet rule. So you might see sometimes that you either don't have enough electrons to give the central atom an octet, or that you have too many and the central atom has to have more than 8. So it is possible. So if you have an atom that's in the 3rd row of the periodic table or below, they can do what's called expanding their octet. And so that means they have more than 8 electrons around them. Now, this is one of those sort of convenient lies that we tell in general chemistry. In reality, it's a little more complicated than this, but in terms of just drawing a Lewis structure for the level that we need to know how to do it, it's perfectly fine to go beyond 8 electrons if you're in if you're in the third row of the periodic table or below, beyond neon, essentially. So you can go beyond 8 if you have to. But what's important to realize is that if you're in the first 2 rows of the periodic table, where you only have s and p valence orbitals available, so that means less than 10, that'd be the first 2 rows, these ones can never expand the octet. All right, so a Lewis structure that involves one of these atoms at the center from the first 2 rows typically will be something like carbon or nitrogen. Those 2 p elements are most commonly seen in those. Those will never go beyond 8 electrons. You want to make sure you don't do that. And if you do need to expand the octet, so if you need to put more than 8 electrons on an atom in the structure, it will only be for the central atom. All right, I've racked my brain pretty hard to think of exceptions to this, and I can't. So if there's an atom in your structure that has more than 8 electrons, it will only be the central atom, never the outer atoms. So once you do this first step up above, completing the octet on the outer atoms, you don't want to add any more electrons to them. Only if you need to extend the octet would it be on the central atom. And there's also 2 exceptions of central atoms that most often do not have even 8 electrons. They have less than 8 electrons. So you might see some structures with beryllium at the center. Typically would have 4 valence electrons, and then the more common one is boron B. Typically would have 6 valence electrons. These are 2 elements that are perfectly fine with incomplete octets. So those are probably the only 2 cases where your central atom would have less than 8 electrons if it's beryllium or boron. Any other central atom, carbon, nitrogen, oxygen, or anything in the third row of the periodic table and below, you should typically have at least 8 electrons around the central atom, sometimes more if you need to, and if it's appropriate to. All right, but we'll see examples of all these different features as we go through, so you won't, all these should be revealed to us and illustrated in a little bit. All right, so that's the third step, how to figure out what to do with the lesser electrons. So let's go through it then with these 3 examples. PCl3 has 26 total valence electrons. Now we're going to distribute the rest of them. So we started with the single bonds to chlorine. That was step 1. And then we said when we're distributing the rest of these, so first of all, how many have we used so far? Well, we've drawn 3 bonds. Each bond is 2 electrons. That's 6 total electrons. We have 20 more to use up. So the first thing we're going to do is we're going to complete the octet of all of our outer atoms, which is chlorine in this case. So we have 2 from the bond. That means we need 6 more around each chlorine to get to a total of 8 for the octet rule. So we're going to put 3 lone pairs on each chlorine. 6 more total electrons, which in addition to the 2 that are shared gives us 8 for each one. So we're going to do that for each one. All right, in this part of the course, you'll get good at multiplying by 8 if you've forgotten your multiplication tables from elementary school. So we have 3 groups of 8 electrons now, 3 octets for each chlorine. 3 times 8 is 24. So we've used up 24 electrons so far, but we have 26 that we have to distribute. So now at this point, any more left over will go on the central atom. So there's 2 more for the central atom to get to our total of 26. Those go on as a lone pair. Okay, so that's how we distribute the rest of the electrons in this structure. And even at this point, we're not necessarily totally done. As we'll see for one of these, we have to do one more step. But this is how we will initially distribute all the electrons. All right, so for NO3-, we had 24 valence electrons. It's charged, so I'll draw it in brackets. So we started with single bonds to each oxygen. And then we complete the octet of the outer atoms first. 2 electrons from the bonds, 6 more in the form of lone pairs. And then after we do that, we need to take stock of where we are. So we've used 3 octets. Each oxygen has 8 electrons now. 2, 4, 6, 8 for each of them. So 8 times 3 is 24. So that's all 24 of our electrons. So in this molecule here, we have negative charge still, but we don't have any lone pairs in the central atom because there's no more electrons left to do that. Now, what you might recognize already is that our central atom does not have a complete octet. It only has 3 bonds, 2, 4, 6. So we're still not done with this structure, but we can't add it as a lone pair because we don't have any more electrons to add. We've used all 24. Okay? So we'll see in a little bit how to deal with that. And then finally, the last one, IF5, has 42 valence electrons. Oops, sorry. So we started with 5 single bonds to fluorine. We complete the octet of each fluorine first. So 6 more dots on each fluorine, 3 pairs, to give us a total of 8, including the bond. So with 8 octets completed, or sorry, 5 octets completed, 8 electrons each, 5 times 8 is 40. So that's 40 electrons, but there's 42 total in the structure, so we still have 2 left. Those will then go on the central atom. And you can see in this case that we had no choice but to expand the octet of our central atom. It already has 5 bonds, which is already 10 electrons, plus the 2 more from the lone pair. So that's a total of 12 electrons around our central atom, which is beyond 8. But in this case, it's fine because iodine is way down here in the periodic table, 5th or 6th row, 5th row I guess it is. So it's fine to go beyond 8 electrons in the central atom if you have to. In this case, we do have to because there's no other way to arrange them without that. So it's fine to do that. So that's that's our only example so far where we expand the octet on the central atom. All right, so that's step 3, as I've sort of outlined things now. All right, and then the last thing we have to do is, in the cases where the central atom does not have an octet, we definitely have to do at least one more thing. So unless it's one of those elements, beryllium, Be, boron, B, that is fine with less than 8 electrons, and if it doesn't have at least 8 electrons around it, we need to fix that. And so that's what we saw with NO3-. We did 3 single bonds, we finished up the octets of all oxygen atoms. And so this nitrogen, as we drew it initially, only has 6 electrons around it. 2 from each of the single bonds, 2, 4, 6. And nitrogen, anything that's in the 2p block except for boron, should have 8. Okay, so if it's carbon, nitrogen, and oxygen at the center, it should have 8. This one only has 6, so we need to do something about that. We can't just add more electrons because this whole thing only has 24 valence electrons, and so we just can't willy-nilly add more. We're going to, so we have to figure out what to do. So the way that we handle this is we're going to take 2 electrons from one of our outer atoms here. We need 2 more for nitrogen. It has 6, it wants 8. So we just need to take 2 electrons from our outer atom and turn them into a shared pair and make it a double bond instead. So what we're going to do is we're going to take those 2 from oxygen and make 1 double bond. So we didn't add electrons, we just changed 1 non-bonding pair into a bonding pair to make a double bond here. That leaves still 4 on oxygen. We took only 2 of those off from oxygen, so there's still 2 other lone pairs left. But now we have this shared pair here that's going to show up as a double bond. So it's still the same number of total electrons. We didn't add or subtract electrons from the structure. We just took 2 that were originally non-bonding and made them into a bonding pair. All right, and now this has exactly 8 electrons around it because we have 2, 4, 6, 8. Each bond counts as 2. The double bond would have a total of 4, plus to the 2 single bonds gives us a total of 8. So that's how we deal with incomplete octets on the central atom often, is we'll remove 1 lone pair and turn it into a multiple bond. In this case, it was just a single lone pair making a single double bond. Sometimes you'll have to do more than that depending on how much you need to do to make up that octet. So sometimes you'll need 2 double bonds to complete the octet. Sometimes you'll need a 1 triple bond, whatever the case is for that molecule. We'll see, but you need to make sure that the central atom has 8 electrons. And that's how we do it here. Yep.
Oh, I was going to ask if you still...
Yeah, the negative charge should always be there. Sometimes I forget to put it. Any other questions? Yep.
If it requires another bond, do you do a triple bond before you do another double bond? Is that what you're saying?
I would say in general that would not be the case. There's ways of evaluating that we're going to talk about here in a little bit, of whether you should, which arrangement is best, whether it's a triple bond or 2 double bonds, and sometimes actually both structures are kind of correct and the real structure is in between those 2, so you would actually draw both of those as sort of like the 2 extremes for that structure. But I would say in most cases, if you have the ability to draw 2 double bonds, you would do that instead of 1 triple bond. The only time you usually draw a triple bond is if there's only one other atom that you can form a multiple bond to, and it has to be a triple bond to complete the octet. But if there's 2 atoms that you could do that, it's usually going to be 2 double bonds instead. But we will talk about how to decide sometimes where those double bonds and triple bonds would go. And so, any other questions on this part so far? So this sort of takes us more or less to the end of drawing a Lewis structure if you're instructed to follow the octet rule. So as I said, you sometimes have to violate the octet rule for the central atom if it's, there's more than 4 bonds, as we saw with IF5. Here we had to draw a double bond to make sure that we satisfy the octet rule. So if the homework question or test question says, consider the Lewis structure of NO3 minus that follows the octet rule, well, this is where you would stop, and for all 3 of those, you would stop there. But then sometimes what we do also is we evaluate what are called formal charges as another way of sort of figuring out, do I have the best arrangement of electrons possible? Now, as the name implies, a formal charge is not a real charge. It's basically just an accounting trick for electrons to figure out if they're arranged in the best possible way. And typically in cases where it matters, should I follow the octet rule or should I follow formal charges, we'll specify that for you in the problem. So if there's any confusion about that, you'll know what we're looking for. Because as I said, in some cases, you just draw the Lewis structure that follows the octet rule and you're done, and that's fine. But then in other cases, you want to say, well, are the formal charges arranged as best as they can be? And that will help you decide if there's anything more you should do in terms of especially like other double bonds or triple bonds that you might need. So what is a formal charge? It's the charge that an atom would have. It's in a Lewis structure specifically. So it's not a property of the atom itself. It's a property of the atom in a Lewis structure. But it would have if the bonding electrons were shared equally. So when we're defining formal charges, we're assuming that we have perfectly covalent bonds, even though in reality many bonds are polar. But if you have perfectly covalent bonds and you figured out, okay, what would the atom's charge be if those bonding electrons were shared equally? Now, the formal definition is not so important for us. It's important for us just to be able to calculate what the formal charge is and how to use it. But that's the formal definition. And another important thing about formal charges is that this Greek letter sigma means sum. So if you add up all the formal charges in the molecule, or the ion, they will equal the total charge of the molecule or ion. So if you have a neutral molecule, so no charge, all the formal charges should add up to 0. If you have an ion with a net charge, all the formal charges add up to whatever the charge is for that ion. And usually in neutral molecules, your best Lewis structure will have no formal charges at all. Every atom will be 0. But sometimes it's unavoidable that you'll still have some formal charges in the molecule, but they have to add up to be 0 if the molecule is charge neutral, like many of them are. All right, that's the sum. Now, how do we calculate it? That's the important thing. So you do it for each atom in the structure. It's not a property of the molecule, and it's not a property of that atom on its own. It's a property of the atom in that structure. So you evaluate it for each atom in the structure. And so the way that you can calculate it is you start with the number of valence electrons that atom has, which we added up at the very beginning of starting the Lewis structure. You subtract from that the number of bonds that atom has, which can be thought of as 1/2 times the number of bonding electrons. Because as I said, in this approach, we're assuming that the bonding electrons are shared equally. So basically you're taking each bond and you're giving 1 to one atom, 1 to the other atom. So you count them that way. And then we subtract from that the total number of non-bonding electrons. Those are unshared, so you don't divide them up or multiply by half. You just consider those in total. So it's those 3 things that you subtract. You start with the number of valence electrons that the atom has, you subtract the number of bonds that the atom has in the structure, and then you subtract the number of non-bonding electrons that the atom has. And that will give you a formal charge. And so what we'll often ask you to do in Lewis structures is to minimize formal charges. Basically have as few formal charges as possible and make sure that their magnitude is not too large either if you do have to have them. And so that's how you calculate it. And then there's some things you can do to deal with formal charges if you want to get rid of them. All right, so here's sort of a summary of how we use that information. So once we calculate the formal charge, how does that information help us in drawing a Lewis structure? So if we ask you to minimize formal charges, so again, usually if it's a problem where that's unclear whether you should do that or not, we'll ask you to do that and then evaluate the structure from there. If you have a neutral molecule, you should have no formal charges at all if possible. There are rare exceptions where it's not possible to do this, but in almost every case, if you have a neutral molecule, there should be no formal charges at all in the molecule if you've minimized formal charges that you're asked to do. But I'm going to remind you multiple times that the octet rule reigns supreme in this case. So you don't want to violate the octet rule to get 0 formal charges. Octet rule is more important. So you have to make sure that your structure follows the octet rule first and foremost. But in most cases, you can follow the octet rule and you can get rid of all the formal charges if the molecule is neutral. There are exceptions to that, but that's what you're usually going to look for if it's possible to do that. If you have an ion that you're drawing the structure of, so we did NO3- earlier, and we'll come back to that in a little bit with formal charges, you cannot get rid of all the formal charges because the sum of the formal charges equals the charge on the ion. There has to be at least one somewhere to get that charge, but you want to minimize how many formal charges you have in the structure and their magnitude. And I would say, I don't like to give like hard and fast rules because someone might find an exception down the road that they can call me on, but at least for the types of structures that we draw or that I've ever drawn even in my entire life, I can't think of a situation where you would have a minimized formal charge situation where the formal charge is either +2 or -2. So if you have to have a formal charge in your molecule, it should be +1 or -1. If it's larger magnitude than that, +2 or -2, that should mean that your charges are not minimized. Sometimes structures that follow the octet rule will have +2 or -2 formal charges, but if you're minimizing formal charges, then you should have only +1 or -1. We'll see how that works later on. So if you want to get rid of formal charges, a common situation you'll see when your formal charges are not minimized is that you'll have a positive formal charge and a negative formal charge right next to each other in the molecule. Basically, 2 atoms are bonded together, one's positive and one is negative in terms of formal charge. So if you have this situation, which we will see in an example later on, none of the examples that we did so far have this, but we'll see this later on. If you have a positive and negative formal charge on adjacent atoms, those can be canceled by making a double bond. So what you would do in that case, and again we'll see this illustrated in later on, I believe, you'll take a pair of electrons from the atom that has a negative formal charge, and instead of leaving it as a lone pair, you'll make it into another bonding pair between those two, like we did for nitrate, NO3-, and so making a double bond. And so that is a way to get rid of both of the positive and the negative formal charge. So that will cancel those two out if they're right next to each other. But as another reminder about what I've already mentioned, the octet rule reigns supreme. So you don't want to do anything to violate the octet rule to minimize formal charges. So you can only exceed the octet if the central atom is in the third row of the periodic table. So if it has atomic number greater than 10. All right. So even if we ask you to minimize the formal charges, you can't violate the octet rule to do that unless it's one of those atoms where it's okay to go beyond 8 electrons in the third row. So you always have to keep the octet rule in the back of your mind. Don't get too focused on formal charges that you're just going crazy with your structure, okay? So you have to make sure that the octet rule is followed, means that the central atom in almost all cases should have at least 8 electrons and only go beyond 8 electrons if you're allowed to do that in the third row of the periodic table or below. All right, so let's go then to the ones that we've already drawn. I reproduced the structures here so I don't have to redraw them myself. And let's calculate the formal charge for every atom in these structures to see how that works, and then see if there's anything else we would need to do to minimize the formal charges. All right, so in this one PCl3, central atom phosphorus. All right, so the way that we calculate formal charge is we start with the number of valence electrons that atom has. That was something that we figured out at the very beginning of all of this when we were totaling up valence electrons to remind ourselves, if we go back to the periodic table, phosphorus is here in group 5, so phosphorus has 5 valence electrons as a free atom. Chlorine is over here in group 7, so chlorine would have 7. All right, so if we go through this, for phosphorus, we had 5 valence electrons. The first number we subtract is the number of bonds that atom has, total number of bonds. So it has 3 single bonds, 1, 2, 3. So we subtract that. And then we also subtract the number of non-bonding electrons that atom has. So phosphorus has 1 pair of non-bonding electrons for a total of 2. So we also subtract 2 from that. 5 minus 3 minus 2 is 0. So in this structure here, the central atom phosphorus has 0 formal charge. If we look at the chlorine atoms, technically each chlorine has a formal charge that we can calculate, but they're all the same because each chlorine has 1 single bond and 3 lone pairs, so they're all identical to each other. So whichever one you calculate, you'll get the same number for all of them. So if we look at chlorine, as we said from the periodic table, chlorine is group 7, so there should be 7 valence electrons. The number of bonds that each chlorine has is 1. It's not the total number, it's the number of bonds that each atom has. So chlorine has 1 bond to phosphorus, and that's it. So we subtract that. And then we subtract the number of non-bonding electrons around each chlorine. 2, 4, 6, 6 total. So we subtract 6. 7 minus 1 minus 6 is also 0. So this is a neutral molecule, and every atom in the structure has 0 formal charges. So there's nothing else we need to do with this. We're good. All right? So that one is totally fine. If we go to NO3 minus, this is going to be the weird one in the bunch. So if we start with this one, nitrogen is group 5, oxygen is group 6. So the central atom nitrogen is straightforward to deal with. It's a group 5 element, so it has 5 valence electrons on its own. It has 4 bonds, 2 singles and a double is a total of 4. 1, 2, 3, 4 lines around the nitrogen. And then it has 0 non-bonding electrons. The nitrogen at the center does not have any lone pairs on it, so there are 0 lone pairs or 0 non-bonding electrons. So that's a 0. We subtract those two numbers from the valence. 5 minus 4 minus 0 is plus 1. So in this structure right now, nitrogen has a plus 1 formal charge. If we look at oxygen, there's actually 2 different arrangements for oxygen in this structure, because this one up here has a double bond and 2 lone pairs. The other 2 down here have a single bond and 3 lone pairs. So there's actually 2 different possibilities for oxygen. We have to calculate those separately. So to keep them straight, I'll call these 2 at the bottom oxygen A. Those are the 2 that have single bonds. And the one up here I'll call oxygen B, the one that has a double bond. So we're going to calculate both of those separately because they may and they will give us different numbers. So for oxygen A, the ones that have single bonds, it's a group 6 element. And then each of these has 1 bond, so we subtract 1. And then each of these also has 6 lone pair electrons, 6 non-bonding electrons total. So 6 minus 1 minus 6 is minus 1. All right, so each of the oxygen atoms that are labeled as A have a minus 1 formal charge. And then for oxygen B, which is the double bonded one, it's still group 6, still oxygen. But now it has 2 bonds, 1, 2. And it has 1, 2, 3, 4 non-bonding electrons, 2 pairs. 6 minus 2 minus 4 is 0. So in terms of formal charge, the nitrogen is plus 1, each of these oxygens is minus 1, and this one is 0. So there's a bunch of formal charges in this structure. Now they should add up to minus 1 because the overall charge is minus 1. 1 minus 1 minus 1 is minus 1, so we did those correctly. And you might be tempted to think, well, okay, we could get rid of some of these, right? Because we have a plus and a minus next to each other. But there's a problem with this one, which is that in order to get rid of a plus and a minus formal charge, we have to draw another double bond. If we try to draw another double bond, we're going to exceed the octet of nitrogen. Right now, nitrogen has exactly 8 electrons, and because it's here in the periodic table, it's in the second row, before atomic number 10, it cannot have more than 8 electrons. So for this structure, we have no choice but to stop. We cannot violate the octet rule to get rid of these formal charges. If we try to do that, if we said, okay, let's make this a double bond instead, now the nitrogen has 10 electrons around it, and that's a severe violation of the octet rule. All right, there's no octet rule police, so you won't get in trouble for that, but you would still get the question wrong on the exam. All right, And so that's where we have to stop here, because any attempt that we would make to get rid of formal charges, the +1 in the nitrogen or in one of the -1s in oxygen, we would have to violate the octet rule to do that. So we stop here. All right. So that's an example where we have no choice but to keep those. But they're all +1 and -1, as I said. You don't want to go, if you had a +2 or -2, you could probably fix that. But +1 and -1, we're going to leave that as that and not go any further. All right, finally for IF5, we'll do this one quickly as well. Both of these are group 7 elements. They're both in the 7th column, second to last column. And then when we look at the arrangement for each of those, iodine at the center here has 5 bonds, 1 bond to each fluorine. And it has 2 more as non-bonding electrons, so 7 minus 5 minus 2 is 0. And then for fluorine, we have, each one has 1 bond, and then 1, 2, 3, 4, 5, 6 additional non-bonding electrons, which also subtracts out to 0. So this is another example of a neutral structure with 0 formal charges, which is usually the case. And so for this one, we would not need to do anything else to minimize formal charges. So all 3 of these structures, the formal charges are already minimized. We can't do anything else to these to make the first and the third have 0 formal charges to begin with. This one we can't do anything else to. So these would be done at this point. All right, any questions on formal charge? Now to illustrate this a little bit more clearly, there's one more thing about NO3 minus I need to cover before we move on, which is the idea of when we drew the structure of NO3 minus, I arbitrarily put the double bond up there. And we had this structure. But you might be wondering, well, why didn't I put the double bond between this nitrogen and that oxygen? Or why not here or here? In reality, all 3 of those are equivalent. So this is a situation where we have what's called resonance, and this can arise when the central atom has multiple bonds, double bonds or triple bonds. So you have double or triple bonds on the central atom. And in some cases, it's possible to arrange those bonds in different ways. Where does the double or triple bond go? And this is a perfect example of that, because we knew that we had to draw 1 double bond to complete the octet, and we just arbitrarily chose to put it up here, but we could have put it in this bond here, we could have put it there. So in reality, all 3 of those are equivalent, and the way that we would indicate that is with double arrows like this, with all 3 structures drawn. So we can have the double bond also down here. So we want to make sure that we still have the same number of total electrons in each structure, no violations of the octet rule, but if we're just moving the double bond around, those are all equivalent and all perfectly valid structures. And the other thing that this indicates, which is a little bit harder to visualize and draw out, but drawing these 3 structures like this, it's not just showing our indecision on where to put the double bond. It's actually indicating something important about the structure of this molecule, which is that it does not have a single localized nitrogen-oxygen double bond. What it has is 1 bond in the structure, which we draw as a double bond, that actually is sort of delocalized, and you can almost think about it moving around the whole structure. It's not really moving, but that's maybe an easier way to think about it, where this 1 pair of electrons here, it's not just between 1 nitrogen and 1 oxygen, it's sort of circling or cycling around the entire structure. So there's no good way to draw that, but you can kind of think about it like this, where you have 3 nitrogen-oxygen single bonds, where those bonds, those electrons are localized between nitrogen and oxygen. Those don't move at all. And then the one that we would draw as a double bond is sort of delocalized over the whole structure, so it can be drawn as sort of like dotted lines. In chemistry, when we draw dotted lines, that's just like our way of saying, like, oh, we don't really have a good way of drawing this. We're just going to put a bunch of dotted lines on there. But the reality is, the way you think about this is that this 1 bond here that's sort of delocalized is not really, it's, each of these nitrogen oxygen bonds is identical to each other. It's not two single and a double bond. It's three identical bonds where you have in between a single and a double. And so you can calculate the average bond order by taking the number of bonds that you have. There's 4 total bonds in this structure, 2 singles and 1 doubles in each of the localized forms, but they're distributed over 3 NO bonds, and so the average bond order is 1 1/3 in between a single and a double. So that's a little bit difficult of a concept to rationalize. We'll talk more about resonance in the next chapter, or it'll make a little bit more sense, I hope. But basically what you have is 3 identical bonds that are in between single and double, and there's no good way to draw that, so we would typically draw these 3 possibilities, which shows that the double bond is not localized, but is sort of cycling around the whole structure. Another analogy that I've seen for resonance, which works for some people but not others, is think about what you get if you cross a horse and a rhinoceros. So that would generate a unicorn. So basically, the unicorn is the real structure, and the horse and the rhinoceros are the 2 resonance structures. So they're kind of like 2 extreme ways of arranging things. Then when you blend those together, so if you blend these 3 resonance structures together, you get the actual structure where you have 1 pair of delocalized electrons. So the resonance is like a hybrid structure where you take, you can only draw out the extremes, but then really it's the blending of all those together that gives you the true structure. Kind of like if you blended a rhinoceros and a horse, you get a unicorn. So I don't know if that works, but that's an analogy for resonance. So resonance is a little bit of a difficult concept for us at this stage, but we'll see more about it in chapter 4 as well. All right. Now the last thing I want to illustrate on this topic of Lewis structures is a little bit more about how we would sort of set up homework and test questions, and how we would either use the octet rule or formal charges as kind of our guideposts for how to draw the best structure. So this is a classic example of a molecule, SO3, where we could ask you first, draw the Lewis structure for SO3 that follows the octet rule. So if we ask you to follow the octet rule, that means that every atom in the structure should have 8 electrons only, and you only go beyond 8 if the central atom has more than 4 bonds. But typically when we say follows the octet rule, we'll mean that every single atom has exactly 8 electrons around it. So if we're going to do that for SO3, let's count electrons first, sulfur and oxygen in this formula. Find them on the periodic table. They're both here in the same column. Both are group 6, so each atom contributes 6 valence electrons to the total. So I did that quickly, but that should be second nature in a little bit. So sulfur, there's 1 in the formula that contributes 6 electrons. In oxygen, there's 3 in the formula that each contribute 6. So that's a total of 18. When we add those together, we get 24 electrons. All right, so if the problem asks us to draw the Lewis structure for SO3 that follows the octet rule, we'll follow the approach that I outlined, but we'll stop as soon as the central atom has exactly 8 electrons and not do anything else beyond that. So in some ways it's a little bit easier because you don't have to evaluate formal charges, you don't have to necessarily draw as many double bonds and things like that. So we'll start with sulfur at the center, single bonds to each oxygen, and then we're going to distribute the rest as lone pairs to complete the octets. So we have 6 more per oxygen to complete the octet. So these steps should get to be pretty fast because we're going to do the same thing for pretty much every one. And now we evaluate how many we've used. So at this point we have 3 octets, so that's a total of 24. Our whole structure has 24, so there's no more lone pairs for the central atom. So at this point here, our sulfur only has 6 electrons, so this does not follow the octet rule because our central atom only has 6, and it's not boron, so it should have 8. So we need to do something to make the octet rule. We're going to do the same thing we do with nitrate, NO3-, which is take off a lone pair and make it into a double bond. Just like we saw for NO3-, we have a choice of where to do that, and in reality all 3 of those are equivalent. So what we'll do is we'll take 1 lone pair and turn it into a double bond. Which one of those you choose is up to you, and that gives us a structure like this. All right, let me make sure I'm setting this up correctly. Okay, good. So for the one that follows the octet rule now, we've gotten to the situation where all atoms have exactly 8 electrons. We completed the octet of the oxygens first. Oops, I left too many lone pairs on there. We completed the octets of the oxygen first, so they all have 8, and now we've added a double bond to the central atom, so that also has 8. 4 bonds, a total of 8. So if we ask you to draw the Lewis structure for SO3 that follows the octet rule, you would stop here. As you guys recognize from doing homework assignments, we can't have you draw things in Blackboard. So usually we would have you draw the Lewis structure and then answer some question about it. How many double bonds does it have? Or we might ask you, what is the formal charge at this point? But this is the structure that you would draw, and then you would answer whatever question we asked about it. But for following the octet rule, you stop here and you don't need to go any further because everything has exactly 8 electrons now. So that's one way we could set up the problem. But we could ask you about the same structure, but ask you to minimize formal charges. So again, you have to read the question closely to know what we're looking for exactly. So if we ask you to minimize formal charges, you would get to this point initially that we just got to, because you have to follow the octet rule. That's non-negotiable. But when you get to this point here, if we calculate the formal charges, we again have a situation where we have a central atom and then 2 different oxygens that we'll call A and B. We have 2 oxygens that are single bonded, 1 that's double bonded. So we have to calculate formal charges for each of those. And so what you'll see is that for the 3 atoms in the structure, we have formal charge all over the place. So oxygen A, each one has a single bond. There's 2 of them there that are identical. 6 valence electrons for each atom in the formula, but now for oxygen A, there's going to be 1 bond and 6 non-bonding electrons around each one. I didn't draw those very clearly, but there's 6. So that's a total of -1. For oxygen B, we have a double bond now, so there's 2 bonds to that oxygen, and now a total of 4 non-bonding electrons. So that gives us 0 for oxygen B. And then for our central atom sulfur, group 6 element also, so 6 valence electrons. It has 4 bonds, 1, 2, 3, 4. Central atom has 0 lone pair electrons, so we subtract a 0, and that's a +2. So clearly we have not minimized our formal charges because this is a neutral molecule, but it has a +2 on sulfur, it has a -1 on each oxygen. So if we ask you to minimize formal charges, especially with that gaping +2 at the center, you should recognize that there's more that we can do. And just like we talked about, if you have a positive and a negative next to each other, you can draw double bonds to get rid of those. So what we'll do is for each of these other sulfur-oxygen bonds, we'll take off 1 lone pair from oxygen and make it a double bond. That's going to get rid of the negative charge, and by doing that twice, we'll get rid of the +2 charge on sulfur. So what we do then is 1 lone pair from each oxygen becomes a double bond, and now we have 3 identical double bonds in the structure. So same number of total electrons, but we've taken off a pair from this oxygen and made a double bond, a pair from that oxygen made a double bond. So now all 3 sulfur oxygen bonds are double bonds, and I'm not going to go through the math again on this, but this one has 0 formal charges. All right, so if we ask you to minimize formal charges, you would then consider this structure, which has 3 double bonds instead of 1. And you have to expand the octet to do that. Sulfur now has 6 bonds around it, so that's 12 electrons, but that's okay because sulfur's in the 3rd row of the periodic table. It's fine to do that for that central atom. So if we ask you to minimize formal charges, you would go to here to get rid of all of them, and this has 0 on each atom. Okay? So any questions on that one? So that gives you an idea of how we might set things up on the homework assignments and exams, where if there's a distinction between octet rule and formal charges, we'll make it obvious to you. All right, we're getting close to the end. Is this the last one? It is. Okay, so just one more example question of how we sort of deal with resonance in a problem standpoint. I mean, some of the problems on the homework assignment or exam will just be like, okay, which of these structures has resonance? And you want to look for ones where you have double bonds that you can move around, basically. If it's all single bonds, it can't have resonance. If every bond is identical, then you can't have resonance. But if you have the situation that we saw before, so that would be just one type of question. Which of these structures has resonance forms? And you just have to sort of draw them out and figure out which ones would have that. But the other thing is sometimes we might ask, I don't think we do this as often anymore, but it's still a good exercise. Which of the following is the most important resonance contributor for ClO3-? So when you go through and draw resonance structures, and this is going to be a another important point for those of you that take organic chemistry in the future is, you draw all these resonance structures out. You can move the electrons around in different ways, double bond here, double bond there, maybe a triple bond, all these different possibilities. You do need to evaluate which ones of those are reasonable structures. You don't want to, because there's always going to be, many possibilities. But if you draw resonance charges that either, mess up your octet rule or, that create a bunch of huge formal charges, they're probably not going to be very important structures, right? It's not a very reasonable arrangement. So you have to sometimes evaluate resonance structures to see, are they important or not? And so the way we do this is sort of in two ways. If we're asking you to evaluate resonance structures and figure out which one is, valid, invalid, more important, less important, and so on, the first thing you want to look at is, do they have the correct number of valence electrons? Because every resonance structure will have the same number and the correct number of valence electrons, are just arranged in different ways. If it's the wrong number of electrons, it can't be a resonance structure for that compound or ion. So let's do it for ClO3-. We have the formula here, so we can count number of electrons. So in my opinion, this is the first thing you do, because you can pretty quickly eliminate some if they don't have the right number of electrons in there. And so let's look at how many there should be. So ClO3-, we have chlorine, oxygen, and a negative charge. So let's find those in the periodic table. We have time, so we'll do that. Cl is group 7. I don't know if we've seen it, but it's in the same column as fluorine and iodine, which we have seen, and we did see it earlier. So that's group 7, 7 valence electrons for chlorine. Oxygen is group 6, each one has 6, plus we have the negative charge. Let's add all those up. 7 electrons for chlorine, 1 in the formula with 7. 3 oxygens in the formula, each with 6. So that's 18. And we can't forget about our overall negative charge, so we have to put one more in for that. And so that gives us a total of 26. All right, so we have 26 electrons total. So any structure that does not have 26 valence electrons is a goner, because it has to have that many valence electrons to be a valid resonance structure for this. So A here, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 24, 22, 24, 26. That one's fine, 26 electrons. B has 8, 8, and 8 is 24, plus 2 is 26. Counted that faster, but that's also 26. C has 8 for each oxygen is 24, plus 2, that's also 26. So the first three all have the correct number of electrons. But if we look at letter D here, we have a little bit of a problem if we look closely. So each oxygen has 8, that's good. That's 24, but then there's only 1 on chlorine here. It's not impossible to have a single non-bonding electron like that, but it's not very common either in the stuff we'll look at. So either way, though, this one only has 25 electrons around it. 3 octets is 24, plus just that one loner on chlorine is 25. It needs to have 26 to be a valid resonance structure. So this one is gone. Okay, so that one we can eliminate based on the number of electrons, but only one of the 4. The next thing you want to do is look at octet rule violations. If a resonance structure violates the octet rule, particularly if it's one that shouldn't violate the octet rule, then it's also not going to be an important one. None of these, though, have that problem. So this one here in A, chlorine has 1, 2, 3, 4, plus 2 more, so it has 10 electrons around it. It goes beyond the octet, but that's fine for chlorine because it's third row. For this one here, we have more than 8. This one has more than 8. So in all cases, your central atom has more than 8 electrons, but it's allowed to do that because it's in the third row of the periodic table. All of the oxygen atoms have 8 electrons, so they're good. So there's no violations of the octet rule here. But it is good to check that, because that's also something that's pretty easy to check, and it can sometimes allow you to eliminate possibilities. So if any of your structures violated the octet rule, if an oxygen atom was missing electrons or had extra electrons, or the central atom had only 6, then you could take it away. The last thing then you can do, if you've sort of eliminated those two possibilities, is we have to look at formal charge next. So if you verify that structures have the correct number of electrons, that they don't violate the octet rule, the only other way to evaluate them is with formal charges. So as I said, first thing is you want to ideally avoid +2 and -2, and then also you want to minimize the total number that you have. So if we look at formal charges for all of these, I'm not going to go through the math in as much detail because I don't want to keep you guys too long here, so we're running out of time. But basically, in this one here, the central atom has a +1 formal charge, and then each of these singly bonded oxygens has a -1. You'll start to see some patterns the more that you do these. If oxygen has a single bond and 3 lone pairs, it's going to have a -1 formal charge. And if oxygen has a double bond and 2 lone pairs, it'll be 0. Okay, so those oxygens are pretty easy to deal with. If we calculate it for chlorine, 7 minus 4 minus 2 is +1. So this one has that formal charge arrangement. For structure B here, we have 2 doubly bonded oxygens, so those are each going to be 0 formal charge. 1 singly bonded oxygen is -1, and then our central atom is also 0 here. So we can recognize that B is a little bit better than A because it has fewer total numbers of formal charges. This one has formal charges on 3 atoms. This one only has formal charges on 1. So if you want to minimize formal charges, you want to have the fewest number of them as well. So B is a little bit better than A because instead of 3 formal charges, -1 +1 -1, it only has 1. It has to have 1 because the whole thing is charged, but that's all it has. If we go to C now, in this case, all of the oxygens are 0 formal charge, and the central atom is -1. So how do we distinguish B from C? Because B here and C both have a single formal charge, a -1. Is it better to have it on oxygen, or is it better to have it on chlorine? And sort of the concept that you want to learn for this type of problem is that, remember that we typically have the most electronegative atoms on the outside. Oxygen is more electronegative than chlorine. It's the second most electronegative atom on the periodic table. So if you have a choice, you would prefer to have negative formal charges on the more electronegative atom. They're the ones that pull the electrons towards themselves more strongly. So if there's gonna be a formal negative charge somewhere, it should be on the atom that's more electronegative. So B is a little bit better in that regard because it puts the negative formal charge on the more electronegative atom, specifically the outer atom is how it's typically going to be. All right, so it's better to have a negative formal charge on the more electronegative atom, which in just about every structure that you'll draw is going to be one of the outer atoms. So if you have a choice between a negative formal charge being on the central atom or the outer atom, it's better on the outer atom because that's typically more electronegative. So choice B would be the best one here, even though all of them, all A and B and C are valid. This one has the best arrangement of electrons. All right, any last questions? Yeah.
So the inside one is positive, is that better?
If you have to have a positive charge, yes, it's better to have it on the central atom than the outer atoms. In this case, we don't need the positive charge because we can get rid of that and make it 0. But if there is a positive charge that you need to have, it's better on the central atom than the outer atom, yes.
I could do for the very last